Welcome, everybody. I wanted to describe optimal transport and its relationship to um, Kantarovich-Rubenstein duality. So this material is all taken from a blog by Vincent Terman that I encourage you to check out. So my favorite paper of mine from the past couple of years is called Metric Reconstruction via Optimal Transport. And it's topology, but it's also topology related to optimal transport and Wasserstein distances. And we sort of cite Kantarovich-Rubenstein duality on page 3. Kantarovich-Rubenstein duality is a pretty pure result about optimal transport. But once you make all your measures involved finite, it just boils down to the duality of linear programming. So I guess what I'm trying to say is this is a formula that's appeared in my papers, and I never really understood it, where it's coming from. But today is the first day that I've understood it, and it's really coming from the duality of linear programming. So I'm excited to share that all with you. So Wasserstein distances between two measures r and theta. You look at the infimum or minimum overall transport plans gamma. So transport plans are just joint probability measures whose marginals give you back r and theta. And you take this integral, or if your measures are finite, you take the sum of how much mass are you moving from point x to point y times the cost of moving that mass that distance, which is just the distance between x and y. All right, so the Wasserstein distance is sort of like an infimum over a transport plan. A transport plan lives on this product space. If r and theta are measures on M, metric space M, then the transport plan is a measure on the product space M cross M. And how much mass are you moving times how far are you moving it? It turns out that this is equal to a quite different formula, which I never understood. This is the content of Kantarovich-Rubenstein duality. So this equality here is the content of Kantarovich-Rubenstein duality. Another way to compute the Wasserstein distance is you look at all one Lipschitz functions on your space and you try to maximize the integral of f with respect to one measure r minus the integral of f with respect to your other measure theta. So that's another way of computing the Wasserstein distance between measures r and theta, is find the maximum over all one Lipschitz functions f of the integral of f with respect to r minus the integral of f with respect to theta. So we'll see from a high level how this comes up. What does it mean for a function to be one Lipschitz? It just means that the distance between the outputs of the function is bounded from above by the distance between the inputs. In other words, if your function was differentiable, then you'd have slope at most 1. So here's the xy plane, and I want to draw a function f of x. And so a one Lipschitz function would never have slope more than 1. Okay, and so the distance in outputs between 2 points would never be more than the distance between the inputs. If, by contrast, you had a function that had slope like 3, then it wouldn't be one Lipschitz, right? Because the distance between two inputs could be 1, and the distance between the outputs could be 3.
Henry, can I ask a silly question?
Definitely.
So if that distance was 3, would it be 3 Lipschitz? Or is the number, okay, cool.
Yeah, precisely. More generally, C Lipschitz means that you have a constant C right there.
Awesome, thank you.
Yeah. All right, so what I hope you take away from this so far is that this is a very mysterious formula for the Wasserstein distance. Somehow, one Lipschitz functions come up, so functions that don't, whose output is sort of difference in output is bounded from above by distance in input. And we seem to have gotten away from this product space. So we don't need to look at transport plans over the product space. We just need to look at the space itself, which is going to give us computational efficiencies. Other questions so far? All right.
I have a quick question.
Yeah, Cameron.
Is there a standardized way to transform a non-one Lipschitz function to a one Lipschitz function that you're aware of?
Well, you could, let's say you had a C Lipschitz function, right? You could replace F with F over C. And then it would be a one Lipschitz function.
Whoa. Okay, cool. Thanks.
Yeah. Some functions aren't Lipschitz for any constant C. So imagine the function f of x equals 1 over x. Right? This function looks something like that. And that's not C Lipschitz for any C, you know, because the slope gets arbitrarily large as you, I mean, the magnitude of the slope gets arbitrarily large as you get close to the vertical axis.
So it just has to be bounded vertically?
Yeah, yeah.
Okay.
You know, but if you have a differential function where the slope it never gets above this constant C, then it's a C Lipschitz, and you could transform it to a one Lipschitz function just by like scaling the vertical axis, divide by C, and then
That factor. Okay.
Right, and then the slope will never be above 1.
That makes sense. Thanks.
Other questions? Alrighty. So yeah, remember one Lipschitz, that'll come up again. As a linear program, this formulation is going to be the primal formulation, whereas this formulation is going to be the dual formulation. So nice connection with linear programming. Okay, so I talked about the primal formulation in the last video, but let me just recap that again. So the primal formulation, we're trying to minimize the cost of a transport plan, subject to the fact that it actually is a transport plan. All right, so here we have our picture of our transport plan. How much mass is being moved from point I to J is just encoded by these entries. Vectorize this matrix to get a vector X. That's our variable encoding the transport plan. We also have all these distances where any entry here just encodes the distance from point I to point J. And you know, the distance from I to I is 0. So that's why I have 0 along the diagonal. So vectorize this matrix to get a vector C of all of our distances. So we're trying to minimize the sum of pairwise products. You know, each pairwise product is how much mass was moved from I to J times the distance from I to J. X, our transport plan, actually has to be a transport plan. So this matrix vector equation AX equals B encoded that for us. Here again was matrix A. When I multiply by vector X, you know, the amounts of mass at each point of the transport plan, I saw that the marginals summing along rows had to give me back the probability measure R, and the marginals summing along columns had to give me back the you know, the probability measure theta. Questions? So when we dualize this, we're going to have a B transpose Y. Minimize is going to become maximize. And this AX equals B and X non-negative is going to become A transpose Y at most C. All right, so the dual maximize B transpose Y subject to A transpose Y is at most C. So let's see what that gives us. Let's ignore the optimization function for the moment and focus on the constraints. So I'm considering A transpose now. This blog likes to multiply A transpose by Y just by writing down matrix A. But of course, we have A transpose in the dual. C, you'll remember, was our vectorization of all the distances. So here's our vectorization of all the distances. Dij is just notation for, the distance between point I and point J. Okay, so when you multiply A transpose Y, you get things of the form, let's see. Yes, you get things of the form fx1 plus gx1 is at most the distance between x1 and x1. Or let's look at this correspondence. You get something like fx1 plus gx2 is at most the distance between x1 and x2. So y is our vector of new variables. We have one new variable for every old constraint. Our old constraints were like marginals in each direction. So we had constraints corresponding to theta and constraints corresponding to r. Those new variables we'll call f and g, the dual variables corresponding to those old constraints. Think of f as a function that you can integrate with respect to measure r, and think of g as a function that you can integrate with respect to measure theta. And so what I'm showing you is each column has 2 ones in it, okay? And so my new constraints are of the form some value of f plus some value of g is at most the distance between the corresponding points. All right, so in any case, I get all the constraints of this form. Some value of f plus some value of g is at most the corresponding distance between the input points. Let's consider this when I equals j. When I equals j, the distance between xi and xj is 0. So I just get f of xi plus g of xi is at most 0. Optimally, once you optimize this dual problem, you achieve equality. So this inequality right here becomes an equality. And so in other words, we get g of xi is equal to negative f of xi. Okay, when this inequality is achieved optimally, you just get g of xi is equal to negative f of xi. In other words, g is just the function negative f. So we're going to replace all of these g's with negative f's and really just think we have one function, f. And when we integrate f with respect to r, we're going to have positive f. But when we integrate f with respect to theta, we're going to consider negative f. So let's take g and make g negative f, because optimally that's what occurs. So g of xj just becomes negative f of xj. And so this constraint now transforms as such. And this looks a lot like what it means for a function to be 1 Lipschitz, right? What it means for a function to be 1 Lipschitz is that the distance between any 2 outputs is at most the distance between any 2 inputs. To really make this the definition of 1 Lipschitz, I would have absolute values here. Okay, and those absolute values come up actually when you just replace I with j. So when I plug in j here and I here, you actually get both terms in this absolute value. All right, so in summary, these constraints, after I dualize the linear program, are telling me I want to consider 1 Lipschitz functions, it turns out. Let's talk a little bit about this optimization function that I'm trying to maximize. So B transpose Y. Y is, Y encodes this function that I'm building. B, if you'll remember, B was our old constraint vector, which is the probabilities in our first measure R and the probabilities in our second measure theta. Okay, so when I look at B transpose Y, I have the value of my function f. Oh, I don't think I want these subscripts here, sorry. All right, so coming from Y, I have the values of my function f, and then coming from B, I have the probabilities in my measure R. And then, this constraint vector B also had measure theta encoded in it. And my original variable vector Y also had the values of this function G. This right here is just the integral of this function f with respect to the finite measure R. It's just an integral of a function with respect to a measure. And same for G and theta. But I sort of told you up above that we can just take f to be, we can take G to be negative f. So when I plug in negative f for G, I get the integral of f with respect to measure R minus the integral of f with respect to measure theta. Okay. So this is what we're trying to optimize in the dual problem. Basically, what's going on is as follows. You have your measure R, okay, and you have your measure theta. They're two different measures, but on the same space. When you're trying to find the Wasserstein distance between them in this dual formalization, you're looking over all Lipschitz functions f, okay, where you integrate f with respect to R, and then you subtract the integral of f with respect to theta. So in other words, take f and then just reflect it to get negative f, okay? And you're trying to maximize this difference. You want to have the maximal possible value of integrating f with respect to R minus integrating f with respect to theta. In other words, you want f to be large where R has large mass, and you want f to be small where theta has large mass, but f can't change too quickly. The slope of f can be at most 1. So we achieve that here, right? F is large where R is large. And here's another spot where f is large near where R is large. But you want f to be small where theta is large, right there, okay? And this, Wasserstein distances take into account, notions of distance on the space, and that enters because f is only one Lipschitz. So you have these competing preferences. Yeah, you want f large where R is large, and you want f small where theta is large, but f can't change all that fast. F is constrained, by distances in your underlying space. Here the real line. All right, so from a high level, what I've given you some intuition for is Kantarovich-Rubenstein duality. This is the integral of f with respect to R minus the integral of f with respect to theta, where f was one Lipschitz. And that is where we started here, okay? The Wasserstein distance is the integral of f with respect to R minus the integral of f with respect to theta, where f is constrained to be one Lipschitz. We have various improvements once we've dualized things. So R and theta were measures supportive size n. In the primal problem, our variable was this transport plan, which had size n squared. But the dual problem has only n variables, right? In the dual problem, our variables are the values of f, this Lipschitz function f, which gave us g, because g was negative f, and this has only n entries in it, right? So we really don't need to go to the product space, right? I don't need to consider this matrix with R one marginal and theta the other marginal, and every entry of this matrix is a variable. My variables are now just the value of f on my original space, not the product space. So that's one nice computational advantage. In the dual program, we only have n variables instead of n squared. Notice that in the dual program, we found the Wasserstein distance without finding a transport plan, okay? So the cost you pay is that when you solve this dual, you do things more efficiently, but you get the value for the Wasserstein distance, but you don't know how to move measure R onto theta just after solving the dual. And then a third final advantage is that in Wasserstein GANs, to train this generative adversarial neural network, you need to train by taking the gradient with respect to theta, one of your input measures. And you can't do that in the primal problem because theta appeared in the constraints. But in the dual problem, theta is really, we have all these probabilities with respect to theta. So theta is really occurring in the optimization function. And so then you can take a gradient with respect to theta because it's in the optimization function into the constraints. All right. So I know there's a lot of notation floating around and a lot of ideas, but there are also some nice pictures. And it's a nice connection between really hard pure math, in my opinion, that I didn't understand even when I wrote papers on it citing this theorem, but then a little bit more applied perspective, the duality of linear programming can elucidate the main ideas for free and can provide computational advantages and advantages for machine learning training. It's a nice mix of pure and applied ideas, I would say, if you're interested in checking it out in more detail. So please do refer to the blog by Vincent Herman, if so. Thanks so much.